Imagine a train, faster than an airplane. China claims its newest maglev concept could reach 620 miles per hour, nearly 1,000 kilometers per hour. That's twice the speed of today's bullet trains, and approaching the cruising speed of a commercial jet. But here's the problem. At those speeds, a train stops behaving like a train, and starts behaving like an aircraft trapped inside a tunnel. And that creates one of the most difficult aerodynamic engineering problems ever attempted. High-speed rail already exists. Japan's Shinkansen runs around 200 miles per hour. China's China Railway high-speed network reaches 217 miles per hour. And experimental maglev systems like the Shanghai Maglev train already hit 268 miles per hour. So why push towards 620 miles per hour? Because distance economics changes completely. At around 1,000 kilometers per hour, rail begins competing directly with aviation. For example, Beijing-Shanghai, 4.5 hours today. At 620 miles per hour, 90 minutes. Which means downtown to downtown travel faster than flying, because airports add hours of security and boarding. But reaching these speeds requires solving a much bigger problem than engines or tracks. The real enemy is air. At normal train speeds, rolling friction dominates. But above 300 miles per hour, something else takes over. Aerodynamic drag. Drag force follows this equation. F_d equals \frac 1, 2 \rho v squared c_dA. Where rho equals air density, v equals velocity, cd equals drag coefficient, a equals frontal area. The key term is v superscript 2. Double the speed, and drag increases 4 times. At 620 miles per hour, the drag force becomes enormous. Visual, graph showing drag versus speed increasing exponentially. To put it into perspective, a 620 miles per hour train would experience similar aerodynamic forces as a small jet aircraft during takeoff. But unlike an airplane, a train cannot climb to thinner air. It must fight that drag the entire journey. And that creates 2 huge engineering problems. Power required increases roughly with velocity cubed. So if a train goes 2 times faster, it needs roughly 8 times more power. Visual, graph showing cubic power curve. That means a 620 miles per hour train could require gigawatts of power, similar to a small power plant. This is why traditional wheel-on-rail trains hit a speed ceiling around 250 miles per hour. Beyond that point, the energy cost becomes economically irrational. Which leads to the next breakthrough. China's design relies on maglev technology. Instead of wheels touching rails, the train floats using magnetic fields. Visual, diagram showing electromagnetic suspension lifting train above track. Electromagnets in the track and train create repulsive and attractive forces that suspend the vehicle about 10 millimeters above the guideway. This removes rolling friction entirely. Now the only major resistance left is air drag. And propulsion works like a linear electric motor. Instead of spinning a rotor, the entire track becomes the motor. Visual, animated linear motor pushing train forward. Electromagnetic pulses in the guideway pull and push the train forward continuously. It's essentially a very long electric catapult. But this still doesn't solve the biggest issue. At 620 miles per hour, the train enters a new aerodynamic regime. When high-speed trains enter tunnels, something strange happens. Air in front of the train gets compressed like a piston. This creates a pressure wave that travels through the tunnel. When it exits, it can produce something called a tunnel sonic boom. Visual, pressure wave simulation moving through tunnel. Japan actually encountered this problem with early Shinkansen designs. The solution? Extremely long aerodynamic noses. Visual, side profile of long bullet train nose. These shapes reduce pressure gradients, allowing air to flow smoothly around the train. But at 620 miles per hour, even these solutions may not be enough. Because air inside tunnels begins behaving almost like a compressible fluid, similar to airflow around aircraft near transonic speeds. And that leads to the most radical proposal. Some engineers propose eliminating air entirely. Systems like Hyperloop attempt to run trains inside low-pressure tubes. Visual, diagram showing vacuum tube reducing drag. Reducing air pressure by 90 to 99% cuts drag dramatically. Which means a train could theoretically reach 600 plus MPH with far less energy. But this introduces massive infrastructure challenges. Engineering rarely gives free upgrades. Every solution introduces new problems. Maglev tracks are not rails. They require precision-built electromagnetic guideways along the entire route. Construction costs can exceed $60 to $100 million per kilometer. Visual, cost comparison chart between rail, maglev, and aviation. That makes national networks extremely expensive. Even with maglev efficiency, aerodynamic drag dominates at extreme speeds. Operating costs could be far higher than conventional rail. Meaning tickets may approach airline pricing. 3. Safety and maintenance. At 620 miles per hour, a small obstacle could be catastrophic. Thermal expansion in the track becomes significant. Control systems must react within milliseconds. Essentially, you're running a vehicle at near aircraft speeds on the ground. China's 620 miles per hour maglev concept is undeniably an engineering milestone. It pushes the limits of electromagnetic propulsion, aerodynamic design, precision infrastructure. But whether it becomes a real transportation network is still uncertain. Because the real barrier isn't physics. It's economics. Airplanes already move passengers at similar speeds, using infrastructure that already exists. For maglev to replace aviation, it must prove it can do something airplanes cannot. Move people faster, cheaper, and more conveniently. Final thought. Throughout history, transportation advances have always pushed against the same force. Not gravity. Not energy. But the invisible resistance of air itself. And the question engineers are now asking is simple. At 620 miles per hour, are we still building trains? Or are we building ground-level aircraft without wings?